Okay, guys, good afternoon. So let's get started. Today's lecture number 2. We talk about hydration. Hydration is the chemical reaction between cement compound, which we learned from last time, and also with water. Okay. Right. So this is what we learned from lecture number 1. This is a major oxide. Okay. Again, try to remember the shorthand for different type of oxide. So some of them could be confusing. For example, C here is for calcium oxide. Okay, it's not for carbon atom in this class. Okay, so this is the major compound which combining two or more type of oxide. As we can see here, C3S. 3 parts of calcium oxide with 1 part of silica. Okay, C2S, C3A, C4AF, and the gypsum. Okay. The particle size of modern cement shows here. So this is the particle size distribution in micrometer. The median size is around 10 micrometer for modern cement. Okay. So if the size is too big, then the core of the larger particles cannot be fully reacted with water. Okay. Cement type. So modern cement has 5 major types. Let's look at this video.
There are 5 types of Portland cement produced in mills like you see here. These different types of Portland cement can be used to suit various design and construction needs. Almost all uses of concrete can be made with type 1, a general all-purpose cement suitable for buildings, bridges, floors, pavements, and precast structures. But some concrete structures require special needs. These precast pipes are exposed to sulfates in the ground. A type 2 cement gives the concrete moderate resistance to sulfate attack. The concrete for this winter placement will set and harden slower. A type 3 cement can be used to give higher strength concrete at an earlier age than type 1. Its application is similar to using a type 1 with a chemical accelerating admixture. The concrete for this dam will generate a tremendous amount of heat during hydration using a type 1 cement. A type 4 cement minimizes the heat for these massive structures. This sewage treatment plant is exposed to high concentrations of sulfates. A type 5 cement gives the concrete protection against these sulfates.
There's 5 major type of cement in the US. Okay. So all the cement sold in the US will meet one of the specs. Okay. The most commonly used specs is ASTM C150. So ASTM is short for American Society of Testing and Materials. Okay. The specs are also jumping into other codes such as UBC, AASHTO codes, and other federal specs. Okay. So ASTM specs, the committee members, including producers, consumers, and the publics, or we call it general interest, such as professors from university. So I'm a voting member of 9 different ASTM standard. Okay. For C150, C150 is standard specification for Portland cement. Okay. So permit 5 different type of cement. Okay. But only 4 of them are widely available. Type 1 cement is called ordinary Portland cement. This is for general purpose. This is by far the most commonly used cement on the market. Okay. In Hawaii, we have type 1, 2 cement, which means it can satisfy the specs for both type 1 and type 2 cement. Okay. So type 2 cement is supposed to be show moderate resistance to so-called sulfate attack. So sulfate attack is a type of chemical reaction which can reduce the durability of concrete. Sulfate from the environment, such as the soil and groundwater, can react with a certain type of chemical in the concrete and cause the concrete to expand and crack. Okay, so we call that sulfate attack. We'll discuss about sulfate attack in much more details in future lectures. Type 2 cement can moderately resist sulfate attack. Can also reduce the heat development, which means this cement can reduce the temperature at early age. Type 3 cement is called high early strength cement. It is normally used in winter time when we do not want the concrete temperature to be too low. If the temperature of the concrete is too low, the concrete will freeze. It is very bad for concrete, especially during early age. Okay, so type 3 cement can be used in winter time and some other applications. Type 4 cement is called low heat of hydration. It will generate lower temperature in concrete. Okay. So this is kind of opposite to type 3 cement. Okay. Type 4 cement is rarely available in concrete, in the US, because we can easily combining type 1 cement with so-called pozzolanic materials such as flash and slag to achieve the same type of purpose for low heat for type 4 cement. The last one is type 5 cement. So the cement is designed to resistant to sulfate attack. Okay. So besides these 5 major types, we also have some subcategories such as type 1A. A is for air entraining agent. So type 1A means type 1 cement with some of the air entraining agent. We'll talk about why we use air entraining agent in cement in future lectures. Okay. So, but remember, we have 5 major types of cement based on ASTM C150. So here's more information from that standard. C150 says the cement must be a hydraulic cement produced by powerizing clinker consisting hydrated calcium silicate, such as C3S and C2S. Okay. And also usually containing calcium sulfate. This is gypsum. So calcium sulfate with 2 water is gypsum. Okay, to control hydration speed, the chemical reaction speed. And no type can have more than 6% of magnesium oxide, MgO. The reason for that is because too much magnesium oxide, it may react with water after concrete hardens, and it will generate magnesium hydroxide. Okay, so this chemical reaction will cause concrete to expand and crack. We call that unsoundness. Okay, we talk more about this later. All right, some other requirement details. It says no cement may have more than 0.75% insoluble residue. Okay, this means less than 1% of the cement cannot be dissolved by water. Also, if low alkali cement is desired, in certain situations such as the concrete may be exposed to alkali silicate reaction or ASR. ASR is another type of chemical attack potentially for concrete. In that case, we may want to use low alkali cement. Okay, so if low alkali cement is desired, then we should have some extra limitation on sodium oxide equivariant. So we can use that equation to calculate the sodium oxide equivariant. Okay, so the purpose for that is to ensure the cement does not have too much oxide, hydroxide. Some other physical requirement for fineness, fineness is equal to the surface area or the particle size of cement. Higher fineness means the cement particle is smaller, has higher surface area. That will affect how fast the cement will react with water. ST time means setting time, and strength development. Okay. You don't have to remember all these details. Okay. So type 1 cement, again, is normal Portland cement, and type 2 cement is moderate sulfate resistance. For type 2 cement, we should limit the amount of C3A bound to the compound to less than 8%. Okay. So why we should do that? And also for type 2 cement, if low heat is the option, we should limit the amount of C3S and C2A to less than this amount. Okay. For type 3 cement or high early strength cement, we should limit the amount of C3A to less than 15%. Okay. For type 4 or low heat cement, we should limit the C3S, C3A, and also we should ensure C2S larger than 40%. Okay. I'm sure it's kind of confusing to you why we should have this kind of limitation. Okay. And for type 5 cement, we should limit the amount of C3A to less than 5%. You don't need to remember all these numbers, 8%, 15%, but you should understand why we should limit the certain amount of compound for different type of cement. Okay, to help you understand that, look at the notes here. The first one is the rate of hydration, which means the chemical reaction speed. C3A will faster than C3S, and then is C4AF. The slowest will be C2S. So this means for the same amount of compound, C3A will generate the most amount of heat. Okay. Then let's look at for type 4 cement, a low heat is the option. Why we should limit the amount of C3A and C3S? That is because C3A and C3S can generate more heat. Okay. If we want low heat, a type 4 cement, we should limit C3A and C3S and ensure C2S, which generate the most amount of heat, to be more than 40%. Okay. Heat of hydration is in the unit of joule per gram. Okay. It can be found in table 4.3 in your textbook, all the details. Okay. But the most important thing for you to remember is the ranking of rate of hydration here. Okay. Then look at the notes number 3. It says the hydration product of C3A may react with sulfate, which coming from the environment, such as groundwater and soil. So that may cause expansion and cracking. We call that sulfate attack. So basically, more C3A, the cement or concrete will be more prone to sulfate attack. As a result, for type 2 cement, which is moderate sulfate resistant cement, we should limit the amount of C2A to less than 8%. For type 5 sulfate resistance, we should further limit the amount of C2A to less than 5%. Okay, so that probably makes more sense to you now, if you can remember why we should limit a certain compound for different purposes. All right. Any questions or comments before we continue? All right. Physical requirement for cement. Okay, this is some further details about the strengths at different age for different type of cement. So we can just look at here. 1 day strength requirement for type 3 cement, which is high early strength cement. So it has a requirement. Then 3-day strength requirement for different type of cement, 7-day and 28-day strength. Okay, just remember they have a strength requirement at different ages for different type of cement. Okay. So the unit megapascal, for 1 psi is equal to about 7 megapascal. Okay. Setting time. Okay, so setting time is how fast the concrete will harden. Okay, we can measure the setting time using a standard method. We have initial set time and final set time, and we'll talk about how we measure that the times in future lectures. So initial set time should be at least 1 hour, and final set time no more than 10 hours. Fineness is the surface area. As you can see, the unit is square meter per kilogram. Okay. The smaller the particle size of cement, then the surface area will be larger. So we see the cement has higher fineness. Okay. A smaller particle size, higher surface areas, that means we have more contact area between the water and the cement. So that will translate into faster hydration. As a result, for type 3 cement, which is high early strength cement, we want smaller particles because it will react faster with water. The maximum sulfate oxide content, the sulfate oxide is coming from gypsum. So gypsum is used in cement to slow down the hydration speed of C3A. Okay, we'll discuss this in a moment. Okay. So that's a limitation of that for different type of cement too. Okay. Okay. So let's look at, this is one examples. Okay. This is the standard requirement based on ASTM C150. This is a measurement for certain type of cement samples. Okay, so we can look at here. We measure the oxides percentage. Okay, the limitation is 20% minimum for silicon oxide, and the test result is 21%. So pass. And also the minimum amount or the maximum amount for different oxide, okay, and test the result. And potential compound. So this is C2S, C3S, C2S, C3A, and C4AF. So this is actually calculated based on the bulk calculation, as we learned from lecture number 1. Okay. So we can estimate the percentage of this compound based on the percentage of this oxide. Okay, so these are the calculated results. And the physical requirement, for example, air content of mortar, test result 8%, limitation 12% max, so pass. Surface area, test result 377, more than 280 minimum. Okay, pass. Setting time, so on. Okay. And here are some of the optional requirements. Okay. C3S plus C3A less than 58%. So that is for type 1 cement. So the test result is 58%. So barely pass. So for type 1 cement, it can be used in most type of applications such as Portland cement pavement, slab on grade, buildings, reinforced concrete bridges. And for type 2, moderate sulfate resistant cement and type 5 sulfate resistant cement, it is used in underground structures, slab on grade, if the groundwater and the soil have a high percentage of sulfate. Okay. For type 3 cement, high early strength cement, it is used in winter construction. As you can see, a lot of snow in here. Again, high early strength cement will generate more heat. That will help concrete to maintain temperature above freezing. Okay. So if the concrete freezes at early age, then the concrete will never achieve its desired strength. So that's one type of application for type 3 cement. Also, it can be used for emergency repair. This is the repair of concrete pavement. So we want the concrete to achieve its strength as quickly as possible. So that's one situation we may want to use high early strength cement. As a result, we can open the road quicker. We can also use high early strength cement in, this is the precast member. As you can see, this is different pieces of precast members. So use high early strength cement in precast plant, we can increase the production rate because we can demold quicker. So we have more production in the same period of time. Type 4 cement. Type 4 cement is low heat cement. When cement hydrate, the temperature inside the concrete will increase quickly. Okay. And remember, concrete is a very good thermal insulator. So that means if we have a mass construction, the inside core of the concrete, the temperature may increase to very high level. If the temperature is too high, it will affect the hydration, change the chemical reaction, which is very bad for concrete. So that's why where we want to use low heat cement when we have mass pouring of concrete, such as this dam or this very big bridge pier. Okay, we want to ensure the temperature inside the concrete will not be too high. So that is type 4 cement. All right, let's look at the chemical reaction or hydration. So when we mix cement with water, chemical reactions will happen. Okay, the cement grain will dissolve into water. Okay, that's three different words. Okay, dissolve, diffuse, and precipitate. Okay, the chemical reaction is exothermic, which means a lot of heat will be released. And heat signature is important to characterize the material development. Okay. Different compound will have different heat signatures. So C2S has very different heat signature compared with C3A, for example. So let's look at the chemical reactions for different compound. Okay. So C3S, C2S. So C3S is tricalcium silicate. C2S is dicalcium silicate. Both of them will react with water and generate CSH. It's the C3S2 and H3. The number here is not fixed. Okay, so it is called calcium silicate hydrate, or CSH. This is by far the most important hydration product in concrete. It provides the strength and also provide the durability of concrete. It will also generate CH. Okay, what is CH? Remember, C is the shorthand for calcium oxide. H is water. Okay, so CH will mean calcium hydroxide. Okay, so C3S react with water, generate CSH and calcium hydroxide. C2S, same thing, but the reaction is kind of different. For example, it will generate less amount of calcium hydroxide compared with C3S. And also the reaction speed of C3S is faster compared with C2S. Okay, this is important. For low heat cement, we want to ensure we have more C2S compared with C3S, okay, because C2S will generate more heat. For C3A, the reaction speed is very fast. So C3A will react with gypsum here, plus water, it will generate ethylene. So this is the one type of hydration product from C3A. Okay. Depending on how much C3A versus how much gypsum, or the ratio of C3A to gypsum, we have other potential hydration product. Okay, for example, monosulfide aluminate, okay, or AFM. Sulfide attack means if we have monosulfide aluminate in hydrated cement, and we may have gypsum coming from the environment after the concrete hardens. Okay, so this reaction here will generate ethylene again. So this is AFT, or ethylene. So we call that ethylene reformation. If that happens, the total volume of the solid will increase, because at that time concrete already hardens. Increase in solid volume means the concrete will expand, and concrete is not ductile at all. So concrete is very brittle materials. If that happens, concrete may crack. So that is chemical reaction for sulfide attack. All right, so let me discuss more about the chemical reaction here. Okay. So this is the major hydration product. One is CSH. Okay. So this one is by far the most important hydration product. So the second one is calcium hydroxide. Calcium hydroxide is weaker compared to CSH, and it is also soluble to water. So it is dissolved under water. Okay. So atrium guide is the third hydration product. Okay. If we rewrite this, so it will become C3A with 3 parts of gypsum and 32 parts of water. Okay, so we can see from here, for each part of C3A, we have 3 parts of gypsum. Okay, so that is why we call that AFT. Okay, so T is called tri. AFT is called trisulfate, okay, which means for 1 part of C3A, we have 3 parts of sulfate. Okay. So T here is for 3 or tri. Okay. For this hydration product, AFM, if we rewrite this, it will become 1 part of C3A with 1 part of gypsum and 1 part of water. And M here means mono. Mono means 1. Okay, so that actually means for 1 part of C3A, we have 1 part of gypsum. Okay, so that's why we call it monosulfate aluminate. A here is for aluminate. F is for ferrite. Okay. For C4AF, C4AF is similar to C3A. Okay, so this is the hydration product for C4AF. It is very similar to AFT. Okay, if we consider alumina or ferrite as alumina, okay, and it will have a similar chemical composition as AFT. And this one is similar to AFM. The difference between C4AF and C3A is it has ferrite. Okay, so the ferrite will play similar role as alumina. So actually, these two are interchangeably. And the reaction is slower compared to C3A, which means it will cause less trouble. More importantly, there's no sulfate attack potential for C4AF. So that is good. Okay, because no lead atrium guide reformation, there's no potential sulfate attack. Okay, so for C4AF, there's no worry about sulfate attack. Okay. So let's discuss about this hydration product. Okay. First of all, CSH. So CSH, that's the name we normally call it, or you can write as C-S-H, or sometimes CSH gel. Okay. Before, people also call that tobermory gel. Tobermory is a natural mineral which has similar structure compared with CSH. Okay. Normally we call that CSH nowadays. Ethylene guy is name we normally call. Okay. Sometimes we also call that trisulfate because it has 3 parts of sulfate, gypsum, or AFT. Again, here T means tri, A is for alumina, F is for ferrite. Okay, in this class, I normally call that ethylene guide or AFT. Okay, 2 common names for this chemical. And this is AFM or monosulfate aluminate. Okay, so M is for mono or 1. So 1 part of C3A has 1 part of gypsum sulfate. So here's some more details about C3S hydration product. Let's just read it together. Don't worry if you cannot remember everything about here. The exams will be open book. Okay, so it is more important for you to understand things than remember things. Okay, and you should know where you can find the information from the slides. Okay, so C3S will produce 3 times more calcium hydroxide for the same molar fraction of C2S. Okay, so this is talk about these 2 reactions. For 2 molar of C3S, if you generate 3 moles of C3 calcium hydroxide, for 2 mole of C2S, it will only generate 1 mole of calcium hydroxide. The CSH generated from C3S will be the same as the CSH generated by C2S. Okay. So here it says the composition of CSH is not exactly C3S2H3. It actually varies depending on many factors. Okay. So it says close to this number. But for example, in the textbook, it writes as C3, S2, and H8. Okay, just remember the number here is not constant, it's not fixed. Here, talk about ethylene guide. Okay, so the ethylene guide, the stoichiometry is not fixed too. Okay, the sulfate may be deficient and replaced by silica or alumina. Okay, so silica and alumina are interchangeable. And for monosulfate aluminate, AFM, okay, it is not necessarily generated by ethylene guide first, as we see from the reaction here. Okay, so actually, depending on the ratio of C3A and the gypsum, okay, so we will have ethylene guide, monosulfate aluminate, combination of these 2 directly. Okay, so it is not usually produced by secondary reaction of ethylene guide with C3A, but may be produced directly from C3A when the sulfate amount is not high enough. In one of the table in our textbook, which is table 4.2, it shows us all different potential hydration product depending on the ratio of C3A and sulfate. It's page 61. 61. Then let's look at how the strength of concrete is affected by different compounds. Okay. For C3A, it will react instantaneously. Okay. As we can see here. Okay. But because C3A will generate ethylene guide and monosulfide aluminate, AFT or AFM, so these two hydration product is much weaker compared to CSH. Okay, so as we can see, the strength is not mainly contributed by C3A. Okay. So the final strength is determined by the amount of C3S and C2S. Okay, but C3S will react much faster, as we can see the curve, the shape. So C3S will achieve around 60–70% by the first week also, as we see here. But C2S, it will slowly go up over more than 3 months. Okay, very big difference. So for high early strength cement, we want to increase the amount of C3S because it will generate CSH at the early age. Okay. So again, remember the rate of hydration is C3 more than C3S, more than C4AF. Slowest is C2S. Okay. And also remember CSH. CSH is the hydration product providing strength of concrete. Okay, so other hydration product, including AFT, AFM, or even calcium hydroxide, does not really help concrete strength and durability. All right, questions or comments so far?
I had a question about AFT and AFM. So I don't understand where the iron is in that. Why is it called AFT or ferrite?
Ferrite. Okay. So
right.
There's a ferrite in the system. It may interchange with alumina. Okay. So F play almost the same role as alumina. So if the system has ferrite, it will replace some of the alumina. Okay, so that's why we call that AFT. Okay.
Thank you.
Okay. All right. So coming back to the cement types. So for type 1 normal cement, okay, this is a typical range. So one example is not like always the same. Okay, so that's a range for that. Around 50% C3S, 25% C2S as well. Okay, for high early strength cement, type 3 cement, we want to increase amount of C3S because it will react faster compared with C2S. For low heat, that's the opposite. We should increase amount of C2S because it is has a slower reaction. This is the adiabatic temperature, which means in the test, inside the container, there's no loss or gain of heat. So measure the amount of temperature, the heat generated by the cement. Here shows the strength development. Okay, so type 1 cement is the blue curve. Okay. As we can see for type 3 cement, early age, the strength, the red line will be higher compared with type 1 and type 4 cement, but the final strength will be lower. For type 4 cement, low heat cement, it is opposite. Early age, up to 3 months, it has lower strength, but later on the strength will exceed type 1, type 3 cement. Okay, this is the table from ASTM 150, shows the limitation for the compound, depending on the type of cement. Okay. As we can see for type 2 cement, the moderate sulfate resistance, we need to limit the amount of C3A. Okay. For type 5, we even further limit the amount of C3A, because C3A it will generate monosulfide aluminate and potentially increase sulfate attack. Okay. For type 3 cement, high early strength cement, we want to increase the surface area because that will ensure we have more contacting area between water and cement. So we have faster chemical reaction. And for type 4 cement, we want to ensure we have more than 40% of C2S because it has slower reaction compared with C3S. Okay. So then let's look at the details, what happened at what different times during the hydration process. Okay. The physical states of cement will change, from full fluidity. Okay, you can mix the concrete and cement readily to true rigidity. Okay, in between these two states, we have initial set time and the final set time. Okay, so initial set time is defined as the time at which the fresh concrete can no longer be handled and placed. Okay, so all the placement and finish the surface of concrete should be done before the initial set time. After initial set time, the concrete is not too fluid. Okay. So for initial set time, it is around 2 to 4 hours. Okay. Again, all the transportation, casting, and the finish of concrete should be done before initial set time. Okay. Final set time is defined as the concrete has enough strength. Okay, the time at which hardening begins, and that's the time to detach the formwork. Normally around 5 to 8 hours. And how we can measure the initial and final set time, we use the so-called Vicat needle. So Vicat is the French chemist who get the first artificial cement in the 1800s. Okay, so this standard test, ASTM CEE688, is after his name. Okay. So we have a mortar sample. We mix mortar sample depending based on the ASTM, and we put a sample, fresh sample inside this container. Okay. And we have a needle with a diameter of 1 millimeter, and also we have a certain weight, and we let the needle to penetrate the mortar sample by its own weight, and we measure the penetration depth using the scale. Okay, so from the beginning to the final set time, so we do that, for example, after every 5 minutes also. Okay, and we get many different dots, and connecting dots, we have a curve like this. The initial set time is the time when the settlement, the penetration depth, achieve 1 inch or 25 millimeter. And the final set time is the time when the needle can no longer penetrate the mortar sample anymore. So 0 penetration. Okay, so very easy to do, okay, but it's pretty time consuming. The water cement ratio for the cement paste is 0.4, which means the mass of the water to the mass of cement is 40%. Right. Then let's look at closely the heat of hydration of C3S. C3S. So that's 5 different stages depending on the rate of heat evolution. Okay. So the first stage is called rapid heat evolution. It occurs within the first 15 minutes after we mix cement with water. Okay. We also call that hydrolysis period. Okay. During that period, a lot of heat is generated, as we can see here. Okay. But after the first 15 minutes, the heat generated will be slowed down. We call that dormant period of stage 2. Okay. So during stage 2, which is around 2 to 4 hours, okay. So not too much going on, not too much hydration product are produced. Okay, so we'll discuss what happened during this stage. Okay. But at the end of this stage 2, the concrete set, the initial set occurs at the end of stage 2 and at the beginning of stage 3. Okay. So at the beginning of stage 3, which is called accelerating stage, then the hydration product produced, such as CSH, calcium hydroxide, HMI, and so on. Okay. So as we can see, the heat generated is accelerated until it peaks at here, and that's corresponding to the time of final set. Again, final set means the concrete has enough strength and it's time to demold the formwork. Okay. So stage 3 is around 2 to 4 hours, 4 to 8 hours, sorry, 48 hours. And then stage 4 is called decelerating stage. Okay. Of course, at this stage, the concrete is no longer workable. Actually, after the initial set time, the concrete is no longer workable. Okay. So that's stage 4. And then stage 5 is called the steady state or diffusion control state. Right. So why we have this different stage? Let's look at the video of the hydration first.
This is a sketch of cement grains suspended in water. The solid hydration products form coatings around the particles of cement and gradually fill the space between. When the coatings first begin to impinge, setting occurs. There is a steady development of strength as the coatings grow together. The amount of strength attained by the mixture of cement and water depends on how effectively the space between the grains is filled up. Concrete will harden within a few hours, but hydration continues for weeks, even years after placement.
All right. So when we mix cement with water, okay, let's say we have a container and we have this is the cement particles, okay, cement, and around the cement is water. Okay. So initially we have a rapid heat evolution because the water will quickly dissolve from the surface of the cement. So we have different type of ions released to the water solution. Okay, so one of the ions is calcium. Another one, major one is hydroxide. Okay, so this ions is released to the water solution. Okay, so as a result, the concentration inside the solution, the concentration of these ions will increase slowly. So this is the concentration of calcium ion, and this is the concentration of hydroxide ions. Okay, but at stage 1 and stage 2, almost no hydration product will be produced. Okay, until initial set time, not too much hydration product such as CSH is produced. The reason is because no hydration product will be produced until a certain level of concentration of these ions achieved. Okay, so I will write this down because it is very important for us to understand the chemical reactions of cement. Okay, so no hydration product will be produced until the so-called threshold concentrations of calcium and hydroxide ions are achieved. Okay, so what happened actually here is during stage 1 and stage 2, why stage 2 doesn't have much going on? That is because during stage 2, that's the process for the concentration to build up. Okay, the threshold concentration here is achieved at here. So at this level or the initial set time, the threshold concentration achieved. Sorry. Threshold concentration achieved, and then we have hydration product produced at stage 3. Okay. And when hydration product produced it will precipitate on the surface of the cement grain first. Okay, and then in a solution. Okay, so that's one of the three works: dissolve, diffuse, and precipitate. Okay, so dissolve means the water will dissolve the ions from the surface of cement. So that's dissolve. Okay, precipitate means the hydration product at end of stage 2 will precipitate on the surface of the cement grain. Okay, and imagine we have more and more hydration product. When hydration product is produced, it will consume the ions, such as calcium and hydroxide. So as a result, the concentration of these ions reduced. So the water will need to dissolve more from cement grain into the solution again. Okay, but because we have hydration product, precipitate cover the surface of the cement grain, the dissolving process will be more difficult. So the water will need to get inside the cement and dissolve more ions back to the solution. Okay, so that's the work diffuse kicking. Okay, so the water will need to diffuse into the surface and dissolve more ions into the solution. So we have enough ions to produce hydration product. Okay, so dissolve, diffuse, and precipitate. Three words. Okay. And the rate of diffusion will become lower when we have more and more hydration product cover the surface of the cement. This is the cement. Okay, so the water need to get in and release more ions into the solution. So the diffusion rate will slow down when we have thicker and thicker layers on the surface. All right, so here some early hydrate forming during the pre-induction period. Okay, so this is a special test experiment using soft X-ray microscope by Professor Montero at the UC Berkeley. Here shows early hydrate of CSH covered on cement grain. So this is a C3S particles hydrated for only 34 minutes. Why we have CSH generated after 34 minutes only? We just learned it should after the initial set time, which is 2 to 4 hours. The reason is because look at the condition here. The solution is saturated lime and calcium sulfate, which means inside the solution we have high enough calcium and hydroxide ions. That means in the solution, the threshold concentration of calcium and hydroxide is already artificially achieved. That's why we see the immediate formation of CSH. Okay, but here I give a very clear picture of the shape of CSH. I call that shape of wheat. Okay. Another picture, this is after 56 minutes. Okay. Again, under saturated lime and calcium sulfate. So this experiment bypassed the second stage using the saturated lime and the calcium sulfate. after 8 hours, 36 minutes, we see not only on the surface of the cement grain, which is here, we also see in situ mass precipitation of hydration product in almost everywhere of the solution. Okay, so concrete hardens because we have enough solid connecting to each other. Okay, so we have more hydration product, both on the surface and also inside the solution. Okay, so needle-like structure connect to the hydration product in the solution, so concrete will harden. Right. So the induction period, the second period, is ended by mass precipitation of CSH, the needle shape. Okay. And early hydrate layers covering the cement grains will transform during the acceleration period, or the stage 3. All right. Now let's just show the reaction of C3S. Remember, we not only have C3S and C2S, but we also have ethylene guide and monosulfide aluminate, C3A and C4AF. Okay, so if you generate ethylene guide and monosulfide aluminate together with CSH, this is more realistic situation happens in hydration of cement. You can just read from here. Not only CSH gel, but also AFT and AFL. Okay, so the cement fineness again is about the surface area. The final step is to grind the cement particle to a suitable size. Smaller size, the higher the surface area, the higher the fineness. Okay. We use the so-called blend fineness to measure the air permeability of cement, so we can get the specific area, which in the unit of square meter per kilogram. So here means for normal cement, for every kilogram, the surface areas of all the particles added together is around 350 square meter. Okay. Okay. So here shows another ESTM standard, CEE688. This is called blended cement. Okay. For example, we blend slag with Portland cement to get blended cement. Okay. There's a slag-based Portland, slag-based and Portland-based blended cement. Pozzolanic materials will be discussed, very soon. Okay. So that include fly ash, not fly ash, there's a typo here, fly ash, silica fume, metakaolin, and so on. Okay. Slag is the byproduct of a steel manufacturing process. Okay. So this blended cement will produce slower strength, similar to type 4 cement. Okay. So that's one of the reasons why type 4 cement is not readily available, because we can easily combine in type 1 cement with slag, for example. Okay. And these cement are environmental friendly because these materials, flash, slag, are industry byproduct. So we replace cement, which generate a lot of CO2 by these waste materials, so we can cut down the overall CO2 emission. Okay. So one of my research focus is to use these waste materials such as slag and flash, we can already achieve 100% replacement of Portland cement using these materials, which means we do not need any Portland cement, and we can produce the concrete with very good performance. Right. So here are just some more details about blended cement, different type. Again, you don't really need to remember the numbers. Okay, you can just read about the details. We'll talk about pozzolanic reaction soon. Okay, so here talk about the pozzolan blended cement. Again, they have different categories such as Portland, pozzolan cement. We have different requirement percentage for pozzolans. Okay, so just a bunch of details. All right. So the general advantage for this blended cement, one is it will generate lower heat, less amount of heat. It may increase the durability. Again, we'll talk about this more. It may increase the liter age strength, and also save the energy and save the environment. Okay. This advantage of this cement, it will require better quality control because slag and flash are with the materials. So how we can ensure its quality, we need better quality control, and also slower strength development. Some more details. Okay, so again, so use these materials will be beneficial to the environment. It will by cut down the CO2 emission, use less energy. Okay, and this material chemically are silicatures or aluminum, has a reactive silica and aluminum. Okay, and we call these materials pozzolanic materials. And here shows what is pozzolanic reaction. Okay. Remember, reaction between C3S and C2S, it will generate calcium hydroxide. Okay, and calcium hydroxide is weaker compared to CSH, and also it is soluble in water. Okay, so pozzolans, including reactive silica oxide, it will react with calcium hydroxide from this reaction. Together with water, it will generate CSH again. So CSH is strong, insoluble to water, so benefit to both the strength and the durability. So transfer calcium hydroxide into CSH. So that's why we like a pozzolanic material. All right. Some specialty cement, which is will not be covered in this class. Just let you know, we have a white cement. Color of the cement is white. We have calcium aluminate cement, which has totally different chemical reactions compared to Portland cement we discussed here. Expensive cement for special application, a rapid set, high early strength cement. This HES cement is different from the type 3 cement we discussed moments ago. So it can achieve high strength in just a few hours. Okay. It is used mainly for emergency repair and precast, pre-stressed concrete. Okay, so that's the end for lecture number 2, hydration. Questions or comments? All right, thank you guys. I will see you Tuesday next week, still online. All right.